Hi and welcome to D.2 Electric and Magnetic Fields. What do I want to say about this? Okay, a lot of the concepts follow on from gravitational fields, which was D.1, gravitational fields. So you'll start to recognise a lot of the relationships and definitions in this topic as well. However, some of it actually looks easier than it is. So for example, if you're asked to draw electric field lines around a charge, you might think, oh, that's really easy. But actually for the exam, then it's not as easy as you might think. There are certain regulations and rules and points and little notes that you might need to know. So unusually for me, I'm going to say I think you should set aside a little time to really go through this tutorial. Know that there are positive and negative charges and predict the direction of forces between them. Okay, so let's start with the very beginning. There are positive and negative charges. Well, if you look at the information below, there are two types of electric charge. There are negative charges that you would find on electrons, and you can see them whizzing around outside of the nucleus of an atom below. And there are positive charges that reside on protons, and the protons are found inside the nucleus of an atom. The electrons, which are negative, are much lighter than nuclei and are easier to move. So in solids, the movement of charge is usually done by electrons. So if you imagine these electrons, they're tiny, they're light, they can be thrown about all over the place, so they tend to move around in solids. Protons and positive ions can bring about the movement of charge in liquids and gases. So in solids, we're looking at electrons making the movements, but in liquids or gases, we can have protons or positive ions moving around within that solution. So we're still on the same learning objective. We've explained that there are positive and negative charges. We'd like to know the direction of force between them. Well, it's really simple. Electric charges experience a force when in the presence of another charge. So if we've got a positive charge here and a positive charge here, they're going to feel a force. And because they're the same, they repel each other. If we had a negative charge here and a negative charge here, because they're the same, they repel each other. So like charges repel. Positive charges and negative charges are different. They're opposite and they attract. So like charges repel and opposite charges attract. So we dealt with the first learning objective that was shown on my sheet. The next learning objective was to solve problems using Coulomb's law. And I'm going to explain to you how Coulomb's law came around just now, and we're going to do some problems on solving Coulomb's law. So, the interaction between two electrically charged particles is due to the electrostatic force between them. So as we talked about earlier, if you have like particles, they feel a force that repels them. And if you have opposite particles, you feel a force that attracts them. Now, Coulomb's law is the law that helps you calculate the size of that force, how strong that electrostatic force is. Let's find out a bit more about Coulomb's law. Wow, well there's a lot of information on this page. Let's go through it step by step. So, the electrostatic force is a vector. So that means we care what direction the force moves in. If it's a like charge, it will repel, and if it's a opposite charge, it will attract. So we know instinctively there are different directions of forces. So it's okay for us to say it's a vector. And it's measured in newtons. Well, of course it is. All forces are measured in newtons. The relationship between the force and the distance is an inverse square relationship. So as you get further away from the charge, the force decreases. So the further away you are, the smaller the force is, and it has a relationship of 1 over r squared, so an inverse squared relationship. If you wanted to write that down, you could say F is proportional to 1 over r squared. The constant, epsilon naught, is the permittivity of free space and is a constant in a vacuum. So the permittivity of free space, I'll tell you a little bit more about in a second, if you'll bear with me. There's a few slides about that. And the final thing about Coulomb's law I want to mention here is that the law only works for point charges with a radial electric field. So you're only going to use Coulomb's law when you're looking at round charges. And we assume that the charge is concentrated all in the centre of that round charge. You're not going to use Coulomb's law for uniform fields, you're only going to use it for fields that are radial. If we look at the formula down there, F equals 1 over 4 pi epsilon naught. That's our constant. Then we have Q1, Q2, and that's the size of the charge on each of the charges we're looking at over r squared. And r squared is the distance between the centre of both charges. Let's keep going with that. Here's our Coulomb's law again, and we want to talk a little bit more about the permittivity of free space. So the permittivity of free space, and this is the little epsilon naught symbol just down that way, it tells us how strongly the electric field reacts to the presence of charges in empty space. And that is just a number. It's just a number. It's got lots of units on the end and all that sort of business, but you just have to think of it as a number. Now, if we were to put those charges into treacle, that number, that permittivity, would be different because the electric field couldn't react as well in treacle as it can in free space. So the permittivity of free space is a number, and that permittivity number changes depending on what material you put the charges in. You don't really have to worry because most calculations are carried out in free space. And that means that your epsilon naught has that value, and if you look down here to the second calculation, you can see the value is 8.85 times 10 to the minus 12. That's a number I talked about earlier. And 4 and pi, those numbers don't never change, they're constants. So that constant of proportionality we use in Coulomb's law, if it's in free space, can be rounded to 8.99 times 10 to the 9, and then all those units afterwards. We don't need to remember them, don't worry. So Coulomb's law can be simplified, if it's in free space, to F equals 8.99 times 10 to the 9, Q1, Q2 over r squared. Let's see if we can do some questions on it. Calculate the force between two charges as shown. Assume they reside in free space. So we know we're using the permittivity of free space for this question. The other thing I'll tell you here is this is a one-dimensional question. It's in a straight line. So we don't have to worry too much about vector addition at this stage. So all you would simply do is you would pop in the numbers. So F equals, it's free space, so we can use 8.99 times 10 to the 9 times Q1, which is 12 microcoulombs, it's 12 times 10 to the minus 6, times Q2, which is 20 microcoulombs, so it's 20 times 10 to the minus 6, divided by the distance between the centre of the two spheres, and that's 105 nanometers. So 105 times 10 to the minus 9, that should be, squared. Don't forget to square it. And the force comes out at a massive 1.96 times 10 to the 14 newtons. Very simple, popping in the numbers, being careful of the magnitudes, and you come out with an answer. This can get a little bit more complicated if we start to look at charges in 2 dimensions. You can see that Q1 is going to experience a force by Q2, and Q1 is also going to experience a force by Q3. So there are some vector additions we have to do there. So let's look at the question. It said, calculate the force experienced by Q1 in this situation. Remember that a force is a vector, and both Q1 and Q1 will be attracted to both Q2 and Q3. Will it be attracted? Yes, they're opposite charges, so yes, it will be attracted. Assume they reside in free space. What does that mean? It means we can use the permittivity of free space. It makes things a bit simpler. So let's look at the answer for that then. How would we do that? Well, you'd have to find the force on Q1 by Q2 first. And you can see the top sum here does that. We have our constant of proportionality because it's free space, 8.99 times 10 to the 9. We have Q1, which is 3 nanocoulombs, times Q2, which is 8 nanocoulombs, divided by the distance between them squared, and that gives us a force of 0.00863 newtons. That's us worked out the force on Q1 relative to Q2. Now we have to work out the force on Q1 relative to Q3. And that's a separate calculation, it's below. So we do the same thing, we plug in the numbers and we come out with a number. The force is 0.0101 newtons. We have two forces and we have to work out what the resultant force is. Well, those two forces act in different directions, and we use a simple vector addition to do that. So we add the two vectors, the force vectors, tip to tail, and you can see that in my triangle below. We have the force of 1 and 2 going up across the way, and the force on 1 of 3 going down the way, and we find our resultant force using trigonometry and vector methods is 0.0133 newtons, and of course it is a vector, we have to say at an angle of 49.5 degrees below the horizontal. So when you find you're using Coulomb's law in 2 dimensions, you need to remember to do the vector addition at the end. We're going to take a little step back and deep dive into the idea of static electricity and charge. We'll look at static electricity in a little bit more detail in a second, but let me just introduce you to the law of conservation of electric charge briefly. And from the name you can pretty much guess what it means. Charge cannot be created or destroyed within a closed system. So if you have a system that's not affected by any other outside charge, then no matter what you do with that system, the amount of charge is always the same. If you look at the situation on the slide right now, we have two charged spheres. One has 5 microcoulombs of charge, one has minus 11 microcoulombs of charge. And if you take the total of that before they touch, it's 5 minus 11 is minus 6 microcoulombs of charge. When you touch the spheres, these charges are going to evenly distribute. The electrons are going to move to where it becomes an even distribution. And when they're removed, then it allows us, using the conservation of charge, to work out what the charge on each of those spheres would be. And if you're lucky, this can be a really nice, easy multiple choice question in paper 1. We're now going to look at something called static electricity. We're going to look at its effect in everyday life and how it's produced. So when we rub a surface, and we have 2 objects here, a polythene rod and a cloth of silk, when we rub those 2 together, what happens is frictional forces start coming into play. And those frictional forces between the cloth and the rod, it removes the electrons from the silk. And because those electrons can freely move, they move onto the polythene rod. And what that means is there's less electrons on the silk, and there's more electrons on the polythene rod. So the silk becomes positively charged, and the polythene rod becomes negatively charged. And that's all due to frictional forces causing the electrons to move from one point to another. Let's move on from the concept of electrons moving from one place to another and the idea of charging by friction to look at charging by induction. It's another way of charging an object. And quite often the exam would look at an explain style question for this. So explain how this sphere can be negatively charged by induction. Okay, so there's 3 very clear steps. Step number 1 is to take a negatively charged rod towards the object. And the effect that has is it moves the electrons within the uncharged object to the other side. It repels those electrons. Step number 2 is then to take an earth wire to the object you're trying to positively charge. And that earth wire removes all those electrons because it feels like it's got an excess of electrons on the opposite side. Step number 3 is to take the earth wire away, and what you'll find is that the object is then positively charged. And what you've done is you've effectively charged an object by induction. From this step, I'd like you to go to your revision note template, write down the 3 steps of how to charge an object by induction, and complete question 7 in the knowledge questions. What is sparking when we're looking at electric and static electricity? Well, sparking is when we have a sudden flow of electric current. How does that happen? Well, do you recognise this here? This is a am I going to spell it right? Van der Graaf generator. You might have seen one in your class. It's the machine where you put your hands on it and your hair stands on end. What's really happening here is this electrode with the brush is causing a frictional force between the brush and the roller. That means that it's gaining an excess of electrons on this side. And those electrons are transferring into this system here, system 1. By gaining the electrons from the brush, that means that this is losing electrons, which means it becomes positively charged. So this area here, number 2, is positive. There's a potential difference, there's a difference in the amount of charge between the hollow metal sphere and position 1. And that difference in potential is eventually going to cause a very large and sudden flow of electric current through the air. Now, the air is usually an insulator, which means that the current wouldn't normally flow through it. But because the potential difference is so great, it breaks down the insulating properties of air, and we get a large spark. That large spark, or the large sudden flow of current, heats the air to very high temperatures and causes it to glow. So what you're actually seeing when we see this sudden flow of current, the spark, is the air is extremely hot. And the size of spark depends on how the separation of sources or electrical charges and their potential difference in voltage. So however big the difference between the positive charge and the negatively charged object is, determines how big the spark is. There are dangers, of course. Let's think about refueling a car or an aircraft. If you imagine inside the fueling pump, the fuel runs through the pipes. And that frictional force, so if you imagine the pipes here, the fuel is running through the pipes. And there is going to be frictional forces as the fuel hits the side of the pipe. That frictional force could create a static charge. In fact, it does create a static charge. So what they do is that any fuel pipe is connected to the earth so that any build-up of static charge is immediately taken away down to the earth, meaning there's going to be no spark, because we do not want a spark in fuel. What happens when we have a spark in fuel? Well, things blow up. So that is not a good idea. So one of the dangers of sparking whilst refueling is that the frictional forces between the fuel and the pipe can cause static charge, and the way they solve this is to earth with a conductor during refueling. Another example of a sudden flow of electric current, or a spark, is lightning. So let's draw a little diagram and see if we can explain it to you. In thunderclouds, friction between atmospheric molecules may displace so many electrons that a charge builds up on the base of the cloud. So can you imagine inside these thunderclouds there are atmospheric molecules, water molecules, all sorts of stuff, and they're rubbing against each other. And what that does is it causes electrons to be displaced. So what we'll find is the electrons might build up on the bottom of the cloud like this. What that has the effect of, because you imagine that the earth is neutral, it's got the same amount of positive and negative charges. But what the effect of the thundercloud is that like charges repel, don't they? So what will happen is that the electrons in the earth will repel away from the thundercloud. And if I redraw this diagram, just bear with me. Like charges repel. Then the positive charges stay where they are. But because the negative charges have been repelled because of the thundercloud, then what we get is a potential difference, because that's positive, that's negative. It's a potential difference. And that potential difference could create a spark or a sudden flow of current that breaks down the insulating properties of air, and it heats the air into a plasma. And that plasma is very high temperature, which causes an explosive expansion of the air, and then it causes thunder. So thunder and lightning all stems from this idea of the frictional forces inside the thundercloud. Those molecules rubbing together and creating a displacement of electrons. The electrons sit at the bottom of the cloud and they push away the electrons on Earth because like charges repel. And that means that the positive ions are left at the top. It creates a potential difference and a sudden flow of current down to Earth. And that's our lightning. But in doing so, in creating that lightning, it heats the air into a plasma, and that causes an explosive expansion of the air, which is then thunder. So it's a really interesting concept, all down to the fact that when you produce friction between objects, it causes the displacement and movement of electrons. One of the learning objectives is to describe Millikan's experiment as evidence for quantization of charge. And I just want to take 2 minutes to explain what quantization of charge means. When we think about charge, we think about a value in coulombs. For example, you might have a positive charge and say that it's got 2.5 coulombs, okay? But we know that those charges are made up by either a number of protons or a number of electrons. And each electron has a charge of 1.6 times 10 to the minus 19 coulombs, and each proton has the charge of plus 1.6 times 10 to the minus 19 coulombs. We know that there's a fundamental value of charge, and that charge is the charge assigned to the electron and the proton. By quantization, we mean that this large value of 2.5 coulombs is made up by a series of building blocks of charge. And that's what quantization means, basically. It's a sum of this elementary charge. So when we're talking about Millikan's experiment, we're saying Millikan discovered that there was an elementary charge and it was built up of all these packets of this elementary charge. Let's look at Millikan's experiment. Here's the apparatus. What we've got is an oil spray being put into a cover. Then there's a tiny little gap. Can you see this gap here? That tiny little gap allows the oil spray, or the little droplets, the tiny droplets of the oil spray, to head into a uniform electric field. And the uniform electric field is between these two large black lines. We can see that it's going from positive to negative, so the positive plates are up here because the blue lines are the electric field lines and the negative plates is down here. The tiny oil drops come into this electric field, and Millikan, here's Millikan's eye here, Millikan was watching these oil drops through a microscope. Here's the method. We've already talked about this tiny electric field, and it's got transparent sides here where the D is, and that allows Millikan to see into this tiny chamber. Oil droplets are in the cover, and while they're in there, they've actually been charged. They've been charged because when they go through the nozzle here, they've experienced friction, and that friction has caused the oil droplet to be charged. Or within this cover, they might absorb or lose ions or charge as they go through the air. So we can assume that these oil drops have a charge, and we don't know what the charge is. Each oil drop enters this tiny chamber, and what Millikan does is he varies the voltage. And what he wants to do is he wants to get one of these little oil drops and he wants it to be perfectly still. And by perfectly still, I'm just going to draw it over here, it means that he wants to balance the weight of the oil drop with the upward force, electrical force, on the oil drop. And we know that the electrical force in that uniform field is equal to QE. So he wants to get to the point where the weight, mg, is equal to QE, and Q is the charge on the oil drop. If it's balanced in midair and he knows the mass of the oil drop and he knows the value of the electric field, he can actually work out what the charge of that oil drop is. And he did this, Fe equals Fg, which is QE equals mg. He did this calculation for a number of different oil drops, all different sizes, all different charges, and he completed this calculation to find out what the charge on each of those oil drops was. And what he found was that the charges on different droplets were always multiples of a certain smallest value. The smallest charge was the same for all droplets. So say he had all these different charges here, they were all a multiple of this initial and fundamental charge. And I think you know what that initial and fundamental charge is. It's called the elementary charge. He came to the conclusion that the smallest unit of charge, which he observed repeatedly, was the charge of a single electron. And this was the first direct evidence of quantization of electric charge. It's his experiment that allowed us to say, okay, all charge is made up of electrons and protons, and also the charge on an electron and a proton is 1.6 times 10 to the minus 19 coulombs. He didn't quite get this exact value in his experiments, and you could see from the previous slide that his apparatus was pretty basic, but he did understand that charge is quantized, and he did get a value very close to the widely accepted value now of 1.6 times 10 to the minus 19. If you'll indulge me, I'd like to go back to the very beginning on electric fields to really explain this in full detail for you. So here we go. We've already said this. When charges are in the vicinity of each other, they experience a force at a distance. So we talked about that earlier. We said, well, like charges will feel a repulsive force, and opposite charges will feel an attractive force. And they're at a distance from each other, so they feel that force at a distance. And the reason they feel that force at a distance is because they have electric fields that surround them. So if an electric charge is electric, it has a charge of positive or negative, it will have an electric field that surrounds it. It's invisible, okay? There are ways of seeing these visually, but they are invisible to the naked eye. We can draw electric fields and represent what they look like. And this is how we do it. So the arrow on the field line shows the direction of the electric field. And I know what you're thinking, how do I know the direction of an electric field? Well, the arrow should always be pointing in the direction that a positive test charge would take. So if you take the top drawing here, we have a positive charge, and if we imagine a positive test charge held very close to that positive charge, it would repel away from it very quickly. So the arrow shows being moved away from the positive charge. At the diagram below, if you look at the negative test charge, if we held a positive test charge near to a negative test charge, it would very quickly, rapidly move towards the negative charge. So the arrow points towards the negative charge. The direction of the field is taken to be the direction of the force it would exert on a positive test charge. So whenever you're drawing electric field lines, just say to yourself, what would a positive charge do? And just follow your instincts. The closeness of the lines shows the strength of the electric field. So if you go to this positive test charge in the diagram shown here, you can see that the field lines are very close as the closer you get to the test charge. That means that the field strength there is very strong. As you get further away from the charge, you'll notice that the field lines get further away from each other, which means that the field strength at that stage is weaker. So the closeness of the lines tells you how strong the electric field is. If you want to memorize some drawings, then, because you may be asked to draw electric fields diagrams for 2-point charges. And really, there are only 3 that you need to memorize, okay? There is, if you have 2 like charges, and you can see them in the top diagrams here, we have the positive charges, they're like charges and they're going to repel each other. So the electric field lines show that. And if you look very closely at the arrows on these electric field lines, they're pointing away from the positive charge because a positive test charge would point away as well. If we look at the like negative charges, the other top diagram, you could see that we have a similar style of pattern of field lines, but this time a positive test charge would want to move towards the negative charge. If we go one below, you can see we have a positive and a negative charge, and the positive test charge would move away from the positive charge towards the negative charge, and it looks a slightly different diagram. 2 things about when you're drawing field lines is that the field lines should always be perpendicular to the surface, and you can see that in my bottom diagram here where I've got the orange arrow. You should try and make them come out of the surface of the charge perpendicularly, and they should never ever touch. They should never cross. They can't cross each other. They should always be either parallel, they shouldn't touch. And I've not done a particularly good job of that on the computer here, but you should never allow your field lines to touch. Okay? We've talked about the radial field, and that is when we have a point charge, and let's go back to that. These are radial fields. We've got point, circular, spherical charges. You'll also find something called a uniform field. And a uniform field is when an electric field is generated between 2 parallel plates. And one plate is positive and one plate is negative. You still have to know how to draw the field lines for that, but they look different. What you should make sure you do when you're drawing a uniform field line is that the lines should still leave the surfaces at right angles. And if you look at my positive plate there, you'll see that the line leaves the surface at a right angle. They should have, the direction of the field is still the direction that a positive test charge would flow. So if we held a positive test charge in this field, it would be immediately repelled from the positive and attracted towards the negative. So it makes sense that our field lines are straight down from positive to negative. The closer together the field lines, the stronger the field. And when you're inside a parallel plate, the field strength should be uniform throughout, and it's often called a uniform field. So the lines should be parallel and equidistant, the same distance between all of them. There is something called the edge effect. So when you get to the edge of a uniform field, they start to sort of bend out a little bit and curve at the edges of the parallel plates. Now we're going to look at learning objective, which is calculate the electric field strength of an electric field using E equals F over Q. Now, how is the electric field strength defined? It's defined as the force per unit positive test charge. E equals F over Q. So there's a formula that you need to know for electric field strength. It's in the data booklet, but more specifically, you do need to know that definition. So the definition of an electric field strength has got to be at the forefront in your brain. Memorize it, okay? Electric field strength, like electric force, is also a vector. But electric force has units of newtons. This electric field has units of, well, let's have a look at the formula. The formula says F over Q. So the units must be the units of F, which is newtons, over the units of Q, which is coulombs. So newtons per coulomb. Units are newtons per coulomb. Remember that definition. We can take that definition and formulate an expression for the electric field strength of a radial field. I'm going to go back just briefly. If you're looking at a uniform field, like I'm showing here, to find the electric field strength, you'd use E equals F over Q or equals V over D, but we'll talk about that later. But you can't really use that F over Q formula for a radial field because your radial field strength has that 1 over r squared quality to it. So when you're looking at finding electric field strength for a radial field, and that's these point charges, we need to apply E equals F over Q to Coulomb's law. So if you'll remember correctly, Coulomb's law said F is equal to 1 over 4 pi epsilon naught Q1 Q2 over r squared. And we want to divide that by Q because E equals F over Q. So I've done some, what I feel to be very simple algebra below to show you what an expression for the electric field strength of a radial field would be. The other expression you can use for electric field strength, and this is for a uniform field, so when you have these two parallel plates as shown, you can use E equals F over Q, and you end up with an expression. You don't need to know how it gets there, but you end up with an expression for E equals V for voltage between the two plates divided by D, which is the distance between the two plates. And what that does is gives us another set of units for electric field strength, because previously we said the units were newtons per coulomb because it was F over Q. But now we've got volts over meters, we can say that our units are volts per meter. So there's two sets of units for electric field strength of a uniform field. As we move on to the higher level content now, we're going to look at two quantities. We're going to look at electric potential energy and electric potential. You'll notice some very strong similarities between the idea of electric potential energy and electric potential in the electric fields. You'll notice the same concepts and the same reasoning behind it is exactly the same stuff as you've just learned in gravitational fields in D1. Electric potential energy. Let's just take it from the beginning. Given that there are similarities between gravitational and potential energy, I just want to do a quick reminder of the gravitational potential energy. We had a large planet, didn't we? And there was a radial field that looked like this. The gravitational field was always pointing towards the centre of the large mass. It was always attractive. And if we took a test mass within that field, then the gravitational potential energy was the energy needed to move a mass away within that field. And it was given the equation EP equals minus G m1 m2 over r. That minus was due to the fact that there was no potential energy at infinity. So we've reminded ourselves about gravitational potential energy. Let's look at electrical potential energy. And actually a slightly different situation, because we're looking at two charges that repel each other. They're like charges. And you can see that the electric field lines are in the opposite direction to that we've just talked about in gravitational field. And in this case, we've got the test charge here. It's positive and it's repelled from the central charge. And actually what's needed, energy is needed to move a charge against the electric field. If we wanted to push the charge that way, we'd need energy to do that. And the stronger the field, the more energy is needed. So we know that our potential energy is directly proportional to the size of the charge. The formula is, and this is for a radial field, EP is equal to K Q1 Q2 over R. Looks pretty much similar to that. But with our gravitational potential energy, we have a negative, and with this electric potential, with the two of the same charges, there's no negative, it's positive. Why is that? Well, work must be done against the repulsive force, which increases the potential energy of the system. The closer the charges are to each other, the more positive the potential energy. So when we have the same charge, our potential energy is positive. When we have opposite charges, the energy is required to pull the charge away. It's required in the opposite direction. And the stronger the field, the more energy is needed. So it's still got that direct proportionality to the charge, but the potential energy decreases because the system loses energy due to that attractive force. So we've still got the same equation, but this time we've got to put in a negative. So for opposite charges, the closer the charges are to each other, the lower or more negative the potential energy. So what is electric potential? Well, the best way to find that out is to learn the definition, because that's what you're going to have to memorise for the exam. Electric potential is defined as the work done per unit charge in bringing a small test charge from infinity, all the way up here, to a point P in the field. And the equation, well, we can work out the equation, but it's given in the data booklet anyway. Work done per unit charge. Work done is equal to energy transferred. And from the last slide, we know that energy transferred was K, Q1, Q over R. And work done over Q is that, they cancel out. So our equation for electric potential is that. You don't have to derive it. It's just, that's the equation for electric potential. It will be given in your data booklet. Why are we saying from infinity? Well, infinity is considered to be a reference point where the potential is 0. By using this reference point, it allows our calculations to make sense. If you remember correctly, the equation for gravitational potential was minus G over R, and that minus was due to the fact that the potential was 0 at infinity. But remember that the gravitational field was only attractive. With electric fields, we have attractive and repulsive. Let's start with the repulsive field. We've got two charges that are the same. Work needs to be done against the repulsive force to bring them together, and this increases the potential energy of the system, leading to a positive electric potential. So when you have the same charges, you calculate the electric potential, and that will be a positive answer. When we're looking at electric potential or opposite charges, we want to separate those charges, and work needs to be done against that attractive force to separate them. That decreases the system's potential energy and results in a negative electric potential. So we're looking at equipotential lines first. What are they and how do we draw them? Then we'll go on to work done. So looking at moving charges or masses between these equipotential lines and looking at the effect that has. Gradients. So how quickly do the equipotential lines change? How quickly does the potential change? And what does that mean in terms of calculations that you would perform in exams or in any form of physical problem? Within an electric field, there are two types of field that you need to be aware of, a radial field and a uniform field. Let's look at radial first. We have a positive charge in the centre of this radial field, and we have these blue electric field lines pointing radially outwards. They are directed away from the charge because if you were to place a positive test charge at any point near that positive charge, it would move away, it would be repelled. And what you can see surrounding this field are some equipotential lines. And I'm going to explain to you what that means, okay? First thing to notice is that these equipotential lines are concentric circles. That means that they are fully circular, as you can see, if you go to the start and work outwards, and the distance between those circles gets greater as they move away from the charge. Now, if you were to place a charge at any point on this equipotential line, so let's place the point here, and you were to travel around an equipotential line, like this, then it stays exactly on that potential line. That means there's no change in potential and there is no potential difference. This means that if you travel around an equipotential line, no work is done. Now let's look at these potential lines in a little bit more detail. Let's give them a value. Let's say that this third line in has a value of 3 volts. This second line in has a value of 2 volts, and this final equipotential line has a value of 1 volt. If I was to move my charge between 1 volt to 2 volt, work is done. Work is done in moving that charge from one equipotential line to the other. And the amount of work done is given by this equation here. Work done equals Q, so that's the charge that you've given this. So if this is an electron, the charge here would be 1.6 times 10 to the minus 19. And the change in voltage would be 1 volt because it goes from 1 volt to 2 volts, so that would be 1 volt. So you can calculate the work done by moving a charge from one equipotential line to the other by multiplying the charge by the potential difference. Now it doesn't matter, let's look at this electron again, draw your eyes to that. It doesn't matter if this electron does this. And then goes on to the second line. It doesn't have to move straight down. It can take any path you like to get to that second equipotential line, and the work done is the same. All the work done cares about is the difference in potential. It doesn't care about the path taken to get there. Now let's look at the uniform field. What we have here is a positive plate and a negative plate. If you were to place a positive test charge at any point within this field, the positive test charges would follow these electric field lines towards the negative plate. You can see that the equipotential lines here are, that's them, I'll label them here, equipotential lines. They're not concentric circles like they were before. They are equally spaced and they're parallel. Okay, so we have equally spaced and parallel lines. Similarly, as before, if you were to take an electron here, or a proton or any charge, any ion, and take it up and down an equipotential line, no work is done. But if you move between the potential lines, equipotential lines, then work is done in moving that charge from one equipotential line to the other. And the amount of work done is given by Q delta V. So I'd like to look at this idea of electric potential and the equipotential lines in a little bit more detail. So you can see that I'm only looking at the uniform field right now, and what I have is a positive plate up here and a plate with 0 volts down the bottom. And I've shown these blue lines here as equipotential lines, and I've actually given them a value. I've gone from 18 volts all the way down to 0 volts. So if I move a charge from here to here, it has a potential difference or a change in potential of 2 volts. If I move a charge from here to here, it has a potential difference or a change in potential of 10 volts. If I wanted to work out what the work done there was, I'd do work done equals Q, take the charge of this ion, whatever it is, and multiply it by the potential difference we've just worked out. I'm quite interested in how that relationship changes with distance though. And what I've done here on the right hand side is I've equated it to a graph. And I've said, let's plot a graph of potential against the distance from the top plate. So as the distance from the top plate increases, how does the potential decrease as we move away from it? And what you can see with a uniform field is that potential decreases at a constant rate with distance from the positive plate. We've got a nice straight line here with a constant gradient. That's easy for us to recognise that relationship there. What you may not be comfortable with and what you may not understand is that the gradient of this graph is equal to the electric field, and I'm going to show you how, okay? Let's take one charge here and drop it down a couple of levels. The work done in doing that would be W equals Q delta V, and we've talked about that equation a number of times. But we can also have an equation for work done with work done equals force times distance, and we'll just give it distance as change in R, and that's the change in R there, okay?
So, wait a minute, if we're looking at an electric field, we don't have to write force, because force equals EQ, doesn't it? So we can put EQ there, and the change in R. So let's equate those two equations. Let's say QV equals EQ change in R. Well, the Q can be cancelled on either side, and we can rearrange that equation to give us, I'm going to go around this way, E equals delta V over delta R. This is the rate of change of potential with distance, or in other words, it's the gradient of a potential distance graph. Let's see if this holds true for a radial graph. This looks a little bit more complicated. Let's go straight to this diagram here, and you'll recognise this as a positive chest charge in the middle, and we have these red electric field lines pointing radially outwards. I've shown the equipotential lines, and you can see we've got some values for potential there as well. It's not quite as easy to draw the potential versus distance graph horizontally, so I've drawn them vertically here. And what you can see is with distance from the charge, the point charge in the middle, the potential decreases very quickly. And you can see that here. There's a large rate of change there. The gradient is big. And as the distance gets further away from the charge, you can see that the rate of change is much smaller. It's not a constant rate like the uniform field was. The potential doesn't fall off at the same rate as it does here. But the rule is the same. The electric field is the gradient of the graph of potential against distance. So at the top bit here, we have a big electric field, and the further away from the charge, we have a smaller electric field. So we can make this whole topic a lot easier by condensing it down into one very simple table. Here's the table here, and I'm going to make it available for you underneath this tutorial as a download. And you have two options. You can either stop the tutorial just now, pause it, and download the table and come back and complete the table with me as I go through it. Or you can watch the tutorial as I'm completing it just now. Try and memorise as much as you possibly can. Try and get a complete understanding of it, and then complete the table on your own later. And that might be the better way of trying to get that information into your brain. Nonetheless, here we are. Here's the table, and you'll notice that we have two columns, a gravitational fields column and an electric fields column. And we have a number of rows down the side which will become a lot more clear once we go through them. So let's get started. We'll start with gravitational fields and look at the top row. It says attractive or repulsive force. So if we have a gravitational force, is it attractive or is it repulsive? The gravitational force is always attractive. Any mass attracts other masses towards it. The electric fields and forces, the force can be attractive if you have two opposite charges, like a positive and a negative, or it can be repulsive. So if you have two like charges, then the force would be repulsive. The next row is asking us for the equation for force between two masses, and for this one we're looking at Newton's universal law of gravitation, and it's F equals gmm over r squared. G is universal constant for gravitation. We've got the product of two masses divided by r squared. For the equation for force between two charges, we're looking at Coulomb's law, and that looks like this: 1 over 4 pi epsilon naught q over r squared. I tend to make this equation much easier for myself by just recognising that this whole 1 over 4 pi epsilon naught is equal to 8.9 times 10 to the 9. So we simplify this equation by saying k q over r squared, and this k value is equal to 8.9 times 10 to the 9. And you'll recognise that the force between the two masses and charges is exactly the same. We've got a constant times the product of the masses, or the product of the charges, divided by r squared. We then look for the definition of field strength. So the definition of field strength with gravitational fields is force per unit mass. And the definition of field strength for charge is force per unit charge. Sorry, that was the definition of field strength for electric fields. The equation for field strength. Well, the field strength is given the term G in gravitational fields, small g, and the equation for field strength is Gm over r squared, and that's for a radial field. For an electric field, the term for an electric field strength is E equals K Q over r squared. And of course, please remember that K is equal to 1 over 4 pi epsilon naught, which is equal to 8.9 times 10 to the 9. The diagram of radial fields. Now, if we imagine we're looking at a planet from very far away, we can see it as a round radial field. And the field lines follow a very distinctive pattern that you'll become very used to. They look like this. The gravitational field is always attractive, so the field lines will be pointing towards the centre of the mass, and you will notice that they are all perpendicular to the surface of the mass as well. For radial fields, for electric fields, we have two different types. We have a positive and a negative. Electric fields travel in the direction that a positive test charge would move. So this radial field looks the same in terms of the lines are in the same place. But in this case, a positive test charge would be repelled from a positive charge. So they would move away from the charge. And if we had the negative charge, the field lines are in the same place, but a positive test charge would move towards this negative charge, like that. The diagram of uniform field, this is quite interesting for a gravitational field. When we stand on the Earth's surface, we don't consider the Earth to be round. We see this, well, largely we see the horizon as straight. So when we're looking at something close to the Earth's surface, we don't consider the field to be radial. We consider it to be uniform, and in which case we draw the gravitational field lines to be straight. They'd be parallel, they'd be equally spaced, and they'd be directed towards the centre of the Earth. You can also make a uniform field for electric fields. You have two plates. One is positively charged, these little positives here. One is negatively charged, and the positive charge would be repulsed. I keep saying repulsed. The positive charge would repel from the positive plate and move towards the negative plate. These lines are equally spaced, they're parallel, and again, they are perpendicular to the surface of the plate or the Earth's surface. It's worth noting that with an electric plates, an electric uniform field, at the end of the plates, we get something called the edge effect, and it's where the electric field is no longer uniform, the lines are no longer parallel, and it sort of bulbs out a little bit. That's called the edge effect, and you find that at the edge of the electric field lines in a uniform field. The field strength equation in a uniform field. So we've got G equals F over M. And you can see, if we go back up to the definition of field strength, we said force per unit mass. So G is equal to force per unit mass. So we come down to the bottom, G is equal to force over mass, force per unit mass. And on that same note, we've said the definition of field strength for an electric field is force per unit charge. So of course, our force per unit charge is our equation. There's another equation for electric field strength, which is V over D, and V is the voltage between the plates, and D is the distance between the plates. I know you think we're finished, don't you? But we have another side to this table, so let's move on to the next side. Units of force and field strength. Well, the units of force is newtons, and the units of field strength is newtons per kilogram. For electric fields, the units of force is newtons, of course, and the units of electric field strength is either newtons per coulomb or volts per meter. So you can use either of those units for electric field strength. So now we're looking at equipotential lines in a radial field. So let's go back to our radial field. I'll try and draw this as neatly as possible. These are just our field lines. These are not the equipotential lines, but we need the field lines before we can draw the equipotential lines. We now have our drawing of the gravitational field lines, and there are parts within this field where the potential is the same. And these surfaces where the potential is the same are called equipotential lines. They are concentric circles. Okay, and similarly for the electric fields, let's just take the example of a positive test charge. Our field lines are going to look like this. Equipotential lines are going to look very similar. And again, these are equipotential lines and they are concentric circles. Moving on to equipotential lines in a uniform field, we draw our uniform field as we did before. That's the Earth's surface. The field lines are equally spaced and parallel. So if we then want to draw the equipotential lines, these equipotential lines are also equally spaced and parallel. And it's the same situation for the uniform electric field. We have a uniform electric field looking like this. Let's ignore the edge effect just now. And the equipotential lines are equally spaced and parallel. Next, we're interested in the work done between the equipotential lines, and the work done between, as we move between these lines here, you have to do work on the mass or do work on the charge to do so, and the work done is given by W equals M delta V, so it's the change in potential as you move between those lines. So you can see the change in potential up here. And for our electric fields, we have W equals Q delta V. And delta V again is the difference in potential between those equipotential lines. When you have a radial field and a uniform field, you can plot the potential against distance. And the graph looks a little bit like this. So this is a radial field. We have potential down here. I'll tell you why it's upside down in a minute. And we have distance here. And the potential at infinity, let's say that goes to infinity, for gravitational field is equal to 0. So the potential at infinity is 0, and it's actually negative the closer you get to the surface of the mass. So your gravitational potential graph against distance is going to look like this, and it goes towards 0 at infinity. So 0 at infinity. And similarly, if you were to go in the other direction like that. Our potential against distance graph for the electric fields is kind of similar, but because we have an attractive or a repulsive force, the gradient or the graph can look either the same way as the gravitational field, or it has a graph that looks like this. And the potential against distance for a uniform field against gravity, again, we're going to start with potential down here from a negative value. So the potential against distance graph looks like that. And the potential against distance graph for electric field depending on whether it's a positive or minus charge, and distance is a nice straight line with a constant gradient. Why am I using the term gradient? Because it's really important to realise that the gravitational field is equal to the change in potential against the change in distance, or it's the gradient of the VR graph. So you can see for the radial field that the gradient decreases with distance from the mass. So that means that the gravitational field strength decreases with distance from the mass. And for a uniform field, the gradient is constant. So the gravitational field strength is assumed to be constant as it moves with distance. Not strictly true with this gradient, this gravitational field one. But if we're looking on a small scale, that is true. And for the electric field strength is the same. It's equal to the gradient of the potential distance graph, or delta V over delta R. So it's the gradient.
Well done for getting this far.
I'd like to define what the electron volt is.
I've actually added in an extra learning objective here, just because when I've been looking at past paper questions, I've noticed we kind of assume that you know this, and I don't think you do.
The energy
so obviously you know how to calculate work
when an
done.
electron
That's W
travels through a
QV.
potential difference of 1
You also know about
electron
joules.
volt.
But do you know how to calculate work done in an electric field?
And that's the amount of energy transferred when
and then present
an electron
your
travels
with
through
electron
a potential
volts.
difference of 1 volt.
I don't think you do. So I thought I'd just go over
QV.
electron volts now
and
to make sure that you're ready for that if it turns up.
Because we're lazy and we're physicists, we write small e, big V. Small e for the charge of the electron and big V for voltage. So 1 electron volt is equal to the charge of an electron, which is 1.6 times 10 to the minus 19, times 1 volt. So our conversion factor is 1 eV equals 1.6 times 10 to the minus 19 joules. Why have we done that? Well, it's just an easier way of explaining things. If an electron has 3.2 times 10 to the minus 19 joules of energy, it's a waste of our energy saying that. Instead, it's easier to say it's got 2 electron volts. It's like if you are running a marathon and you say, oh, well, I ran, I don't know how many meters a marathon is. I ran 32,151 meters. You wouldn't say that. It's confusing. You just say I ran 26.2 miles. So it's just a unit of energy that makes things easier for us to convey to other people. That's what an electron volt is.
I've given these two definitions their own little section because I've actually seen most exams in the past allocate 1 or 2 marks to these definitions, either as a multiple choice question or as straight out, what is the definition of a volt or voltage. So let's just look at these definitions in more detail and pop them in our revision notes. Okay, first of all, let's have a look at some terms. Energy, again, has units of joules. Charge has units of coulombs. And potential difference has units of volts. Do you remember this equation? E equals VQ. Sometimes written as W equals VQ. That's an equation for energy in electrical circuits or electrical appliances. Well, if we rearrange that for V, so V is the subject, what we have is V equals E over Q. And basically, the definitions of voltage and the definitions of the volt, which is the units of voltage, are gleaned from this equation here. So if you wanted to find voltage, you'd basically describe this equation in words. So you'd say voltage is the energy transferred per unit charge passed. Per means divided by,
Okay, so voltage is the energy transfer, that's on the top, divided by per unit charge. See how it works? And the volt, well, let's just look at the units of these things. 1 volt is equal to 1 joule per Coulomb. 1 Coulomb. These two definitions are important. Let's pop them into the definition section. So voltage, I don't need to write this down, you can do it. So you write down your definitions here.
Magnetic fields. This is a tricky topic, so let's take as much time as we need to go through all of this topic right now. So we'll start off with, what is a magnetic field? Well, a magnetic field is a region where the force of magnetism acts. If we look at this bar magnet here, we can see that there's a north side of the bar magnet and a south side of the bar magnet. And there are invisible field lines that loop around from the north, pointing towards the south. These magnetic field lines show the direction of the field at any point, and they also show us how strong the magnetic field is. If the magnetic field lines are very close together, it's a strong magnetic field. And if we go to the side of the bar magnet here, if they're very far apart, then it's a weak magnetic field. These magnetic field lines should never touch. And in the terms of a bar magnet, what they do is they loop round towards from the north to the south. What's in fact happening here is a bigger loop going round, coming back, and a loop going off to infinity, but ultimately coming back towards the south side. The magnetic field is a vector, so we really do care about the direction of this. There are a couple of patterns that you should be familiar with, and these patterns of bar magnets are in particular quite important. You should be able to draw these bar magnet patterns. You've seen this one before, this was on the previous slide. And it's important that you have the loops going from north to south and that they do not touch at any stage. When we have two poles of the same, so north facing a north, we know from experience that these magnets will repel each other, and this has to be reflected in the magnetic fields. So the magnetic fields will repel each other as they come out of the north, and they'll ultimately loop round back into the south again. When we have an opposing poles, so north and south, we know from experience they will attract each other, and this has to be reflected within the magnetic field lines. And you can see that the north field lines then travel towards that south there and form in a loop pattern, and then ultimately go back towards their own south pole. It's not only magnetic materials that can produce a magnetic field. A magnetic field can be produced by a long, straight wire. And in this situation here, the long straight wire is shown as this grey wire pointing upwards. Any wire that has a current flowing through it will produce a magnetic field around it. And you can see this magnetic field is made up of concentric circles. And as we go further away from the wire, those circles start off very close together and the density of the field lines is very close, which means it's a strong magnetic field. But as you move away from the wire, the density of the field lines decreases, meaning the magnetic field weakens as it goes round. There's a rule called the right-hand grip rule, which allows us to find out what the direction of the magnetic field is. In the previous slide, when we looked at the bar magnet, let's go back, we knew that the direction of the magnetic field was from north all the way around to south. But if we go to a wire with a current flowing through it, there's no north and south. We don't know what direction the magnetic field is. So the right-hand grip rule allows us to determine that. And what you do is you take your right hand and you form it into a thumbs up shape. You point your thumb in the direction of the electric current, and your fingers will curl round in the direction of the magnetic field. So as shown on the slide here, you can see that the fingers are curling round anti-clockwise, and thus the magnetic field has concentric circles going anti-clockwise. You should be able to draw this magnetic field of a long straight wire. This is a pattern that you need to be able to draw and in the correct direction. Another magnetic field pattern that you should be able to draw is that of a solenoid. And what a solenoid is a series of circles or coils of wire, all connected to a power source, a direct current power source. And if you look at the magnetic field line patterns of this solenoid, you see that the magnetic field lines come out of one side, loop around and into the back, and ultimately they loop around into infinity and back towards it again. In fact, this pattern looks a lot like a bar magnet, except for in the centre, where we can actually experience the magnetic field in here. And what we find inside the centre of the solenoid is a uniform-ish, as uniform as possible, a uniform magnetic field. So the lines are straight and they're equally distanced apart. We can find out the direction of the solenoid by using the right-hand grip rule.
You will see that we've suddenly changed a different recording angle, and it may seem a bit odd at first, but why? Why have we done this? Well, I want to introduce my friend. Oh, my hand. I want to be able to show you my hand as we're going through this demonstration. The right-hand grip rule is super useful when we're dealing with solenoids. We can find the direction of magnetic fields using this very simple rule. So let's look at this question. Using the right-hand rule, predict the direction of the magnetic field at point A and B. So let's go with point B first. We pop our thumb in the direction of the current and our fingers curl round in the direction of the magnetic field. That means that where my fingers are pointing is where the magnetic field will point out of the solenoid. So we'll find magnetic field lines going in that direction at point B. And if we turn our thumb around the other way, my fingers are curling round in that direction, again in that direction. So at point A, we'll have field lines coming in here and coming out there. Let's just check the answer for that. There we go. Simples.
Now we know how to find the direction of the magnetic field. There are a couple of other things that are important about a solenoid, and namely how we can increase the strength of the magnetic field. How can we make these magnetic field lines, more of them and closer together? Well, we can do so by increasing the number of coils in the solenoid. We can introduce a core, a soft iron core into the centre here. So instead of leaving it full of air, we can put a soft iron core in there. And what soft iron does is it magnetises in the event of a magnetic field being placed near it. So that strengthens the magnetic field inside the core of the solenoid. And the third thing we can do is increase the current moving into the solenoid. A solenoid is much, much better than a bar magnet because you can vary the strength and you can switch it on and off. Both very useful qualities of the solenoid compared to the bar magnet.